The binary addition Turing machine is fairly complicated. It's not that complicated a function. It's one that we all know how to compute. But in terms of sheer number of states and number of transitions, it is definitely more complicated than anything else we looked at. It lets me make a point, though, about the possibility for simplifying things using multi-tape Turing machines. Now, your textbook covers multi-tape, makes the point that a multi-tape machine can be simulated using a single-tape Turing machine. Therefore, there is nothing you can compute with a multi-tape Turing machine that cannot, in theory, be done with a single-tape Turing machine. Obviously, if you have a multi-tape Turing machine and you only use one of the tapes, you've got a single-tape Turing machine. So there's nothing you could compute with a single-tape Turing machine that you could not also compute with a multi-tape one. So adding the additional tapes does not actually alter the computing power of a Turing machine. The reason that multi-tape machines are worth keeping in mind is because, at least conceptually, there are some problems that are simplified considerably if you allow yourself the luxury of the multiple tapes. That said, I personally find programming multi-tape machines to be much more finicky. Part of this is because they don't actually process the tapes in straight parallel as much as one step at a time, and because of that, there's this interesting problem that all too common arises when you get your different tapes sort of out of sync by one position. It's very hard to resynchronize since every tape wants to be moved at least one space on every transition. This is why some authors actually relax the requirement that the Turing machine always move the tape either left or right one space, and also allow an option for staying in position. But we're going to stick with the textbook's convention saying that Turing machines have to move back and forth. Nonetheless, I think this example of binary addition works very well with a multi-tape machine. We're going to use 3 tapes. The first 2 tapes will hold the input numbers to be added, and we will assume, as we did before, that these numbers have equal number of bits, and then we will use the third tape as the output area for our summed number. So the first thing we would want to do if we were doing addition, and think of doing addition of 2 binary numbers on paper, we always start at the rightmost position. But by convention, Turing machines always start at the left. So the very first thing we're going to need to do will be to move to the far right of our 2 input numbers. All right, if we were moving to the far right on a single tape machine, we would do that by simply saying, if you see a 0 or a 1, move to the right without changing the number and keep going until you hit a blank that will signal the end of the input. Now, transitions for multi-tape machines are a little bit more interesting because we have to write a transition rule for each of the 3 tapes. So we will say that if we see a 1 on the first tape, we will write a 1 and move to the right. If we see a 1 on the second tape, we'll write the 1 and move to the right. And we shouldn't be seeing anything at this point except blanks on the third tapes. So this gives us a single transition on 1s on basically both tapes. We also have to consider the possibility that one tape would be looking at a 0 and the other one would be looking at 0s. And then there's the possibility that one tape would be looking at a 0 and the other would be looking at a 1. or vice versa. All right, those transitions should shift us to the right until one of our input tapes no longer is looking at a 1 or a 0. In fact, at that point, we would expect all of our tapes to be looking at blanks, and we would want to shift back to the left, or excuse me, yes, actually to the left, so that's the wrong transition. Shift back to the left. And now we have just repositioned our tape heads so that we are pointing to the rightmost digit in our binary inputs. Now we're actually ready to do addition. If we were doing addition on paper, we would simply look at the digits in our current column, which is currently the rightmost one, and we would say, well, if we see 2 zeros, we're going to have 2 zeros on output. So let's go ahead and say that. If I'm looking at a 0 on the input, we'll leave it alone. Move to the left. If I'm looking at a 0 on the other input, we'll leave it alone. But shift to the left. We should be looking at a blank on the output tape, but we're adding up a 0 plus a 0, and the answer to that is 0, after which we shift to the left. And somehow I got a parentheses in there. Try that again. 0, 0, left. All right, there we go. What happens if we're looking at, let's say, a 0, 1 or a 1, 0? Well, if we're looking at a 0 on the first tape, we'll leave it alone, shift to the left. If we're looking at a 1 on the second tape, we'll leave it alone, shift to the left. 0 plus 1 is 1, so we write a 1 on our output tape and move that to the left. And then we take the symmetric case. We're looking at 1 on the first tape. And a 0 on the second tape. Again, 1 plus 0 is 1. All right, so that's 3 of the 4 possibilities. Now the fourth possibility is that we would be looking at a 1 on both input numbers. 1 plus 1 gives us 1, 0. And falling back on our old grade school habits, we would say, so we put a 0 in this column and we carry the 1. And so notice that all of our addition so far has been based upon the notion that we would not, in fact, have a carry left over from previous columns. If we had a carry, 0 plus a carry would be 1, not 0. So we're going to need really a separate processing state to handle the notion of a carry. So let's go ahead and create a state for that purpose. And we will say that if, in fact, we were looking at a 1 plus a 1, so 1 on the first tape, 1 on the second tape, we will write a 0 into this position in the output, but state Q2 is going to be our place that we come to in order to do additional additions that involve carries. And so if we were in state Q2 and we were to see, for example, a 0 in both tapes, then 0 plus a carry is actually 1. But this actually isn't correct, because if we have 0 on both tapes, we would write a 1 and there's no carry. So actually we want to come back to state Q1 on that. So let's actually redo that. 0 on the input, 0 on the input. Continue shifting left. On the other hand, if we saw 1s in both inputs from state Q2, one plus 1 plus 1 from a carry would be 1, 1. And so we would write a 1 into this position of the output and stay in the carry state. Similarly, if we saw a 1 and a 0 on the input, one plus 0 plus a carry is 1, 0. So we would write a 0 in the output, stay in this state because we still have a carry. And symmetrically, if we saw 0 plus 1, 0 plus 1 plus a carry is 1, 0. So we write a 0 here and stay in the carry state. All right, so that should handle things. Let's test that much and see how well it works. So let's say we give it the input 0, 1, 1 plus 0, 0, 1. And we'll leave the third input tape blank. So the first thing that's going to happen in Q0 is we should be moving to the far right. Until we hit blanks in the inputs when we transition into Q1. Q1, now we are adding 1 plus 1 with no carry. And the answer should be 0. You can see that written down into the third tape, but we had a carry from 1 plus 1. And so now we are in state Q2. Q2, now we are looking at 1 plus 0 with a carry, which is 0 still with a carry. Now we're looking at 0 plus 0 plus a carry. And 0 plus 0 plus a carry is 1. And actually moves us back to state Q1 because we have no carry. Now we're done with our inputs and we're looking at blanks. So this is going to be our signal that we're actually done with input, is when we've processed all of the numbers, added them up, and we've started to hit blanks on the input. So let's finish up our machine by adding a final state for when we're done. And from Q1, for example, if we see a bunch of blanks, we just say we're done. It's just a little bit trickier coming out of Q2. If we're in Q2 and we see a bunch of blanks, that means that we had probably a pair of 1s in our leftmost column. And so we wrote a 0, but we've still got a carry left over. And so we need to remember to write that very last carry digit out to our output. So let's actually try that case. Suppose we do 101 plus 110. First we step off to the right of our inputs. Now in Q0 we're looking at 1 plus 0. That's 1 with no carry, so we stay in Q1. Now we're looking at 0 plus 1, which is 1 with no carry, so we stay in Q1. Now we're looking at 1 plus 1, which is 0 carry 1, so we move to Q2. Now we're looking at blanks, but because we're in the carry state, our instruction says to write a 1 onto the third tape, and so we get the very proper 1011 as our output, and we're done. So the thing to take away from this is that, as messy as it is trying to manage transitions on multiple tapes all at once, overall, conceptually, this machine winds up being a lot simpler than the single tape version that we wrote to accomplish the same function. It's much more intuitive. We can think about working in columns, things that were supposed to be matched up in corresponding parts of the numbers we can handle more naturally through the movement of the various tapes. This is not to say that multi-tape machines are always easier than single tapes. Not by any means. But for certain problems, you can actually simplify your view of how the Turing machine works if you have the multiple tapes available.